And I'll briefly touch upon this, towards the end. But first, what happened? Great. So first, let's define what I mean by real-time machine learning. And to describe the concept and our perspective on this, I'll use a few examples again and again in the presentation. These are obviously just examples, and hopefully the concepts apply to many more verticals and domains. So one example we'll sometimes talk about is credit card transaction fraud. Let's say you go to a store, let's say you go to Safeway, you buy some groceries. Visa has a few hundred milliseconds to decide if this is a fraudulent transaction or not. And within that, they have to load a bunch of data, they have to run a bunch of models, things need to move over the wire. All of that needs to happen while you are waiting for the swipe to go through. Another example we'll use is, let's say you opened your TikTok feed or Facebook feed, or some e-commerce product, and they are trying to give you your personalized list of things or content that you should be consuming. And some machine learning system is making a decision, once again, in 300, 400 milliseconds to decide what content or what product should be shown to you. And the third example that we'll sometimes talk about is someone just applied to for insurance, and some machine learning system is going to do underwriting for that and would generate a personalized price quote for the person who applied for insurance. And there are lots of signals that go into any of these models. If you have worked in insurance, you'd probably understand this. But one of the many things that might go in this is, what is the probability that this user is going to submit a claim that's in the next 6-9 months? And there's a model specifically for that. And you have to make a decision for that model in addition to a bunch of other models as well. There are 4 stages of real-time maturity of organizations out there, from what we have seen very broadly. Obviously, it's a spectrum. In stage 1, everything is batch. Your data is collected, cleaned, processed in a batch manner. You extract features out of it, Airflow pipelines, DBT, those kinds of things. You do batch prediction. Those batch predictions are once again used by downstream batch processes. Everything is batch oriented. What we call a stage 2 is your features are still computed in batch. Maybe let's say once a day, once a week, some frequency like that. But model scores are not computed in batch. Models are served on demand while the user is waiting. What is the point of that, you may ask? Let's say the models are very costly, and running this for every user or every possible transaction is hard. In case of credit card transaction, as an example, you could compute a bunch of things offline, but the model absolutely needs to run while the transaction is happening. You cannot even know what transaction might happen in the future. So systems of this class are stage 2. Stage 3 systems are those where not only the inference is happening real time, the features are also happening real time. And what I mean by that is, you're looking at data that was coming in a few seconds, a few minutes ago, and using that to reflect the features, which then shows up in the model decision, because the model is also running offline. Notice that in stage 2, even though the model inference is real time on demand, the models are still trained fairly infrequently. I was at Facebook before this. Even at Facebook, we had a very large, like literally thousands of models that were not retrained for months at a time. And so that is the common scenario, certainly for stage 2. But that is also the scenario for stage 3. Even though your features are real time and your model inferences are real time, your model training is still happening on intervals, usually once every several weeks, several months, depending on how important that use case is. And stage 4 is where the model training is also happening online. And what that means is, literally, as new data points arrive, a gradient, gradients propagate, gradient descent happens. And within a few seconds, the model weights are changing. And this is continuously happening as new information is being made available to the model. Different teams, different companies are at different stages of maturity. Some of them are at stage 1 and some of them are at stage 4. And there's often a wide variety within a single team or a single organization as well. You may have use cases that are stage 1, and you may have some use cases that are stage 3 or stage 4. If, let's say, you're working on churn prediction, which is a very internal, non-user facing application, a lot of those might stay in stage 1. Whereas if you are, let's say, working on recommendations or let's say fraud detection or insurance or lots of these other use cases, which often impact top line, bottom line, you'll probably in further stages of this graph. What we have seen in our experience is stage 4 is still a bit far away. Most companies, most teams have not adopted online training yet, and even at FANG, there are maybe like 20 models that are online trained or 10 models that are online trained. Most other models are not online trained. So online training is a few years away at the very least at this point of time, if it ever becomes a reality. However, what we have started noticing is more and more teams and use cases have started shifting from stage 1 towards stage 2 and stage 3. In fact, stage 1 is beginning to die out unless you're working on an internal non-user facing application like churn detection. For all user facing applications, a lot of them have started moving away from stage 1 towards stage 2. And some of the more mature, advanced teams out there, they are already at stage 3. But very few people are on stage 4 right now. So this is the, when I say, real-time machine learning is here to say, this is, what we mean. And I'm usually picturizing stage 2 or stage 3, not stage 4 in the rest of the conversation. All right. So with this, now let's look at, why are people making the switch from stage 1 towards, stage 2 and stage 3. I'll go through a bunch of examples and a bunch of, reasons, all of which mutually, push people in this direction. And one thing I want to clarify is I'm not here to convince you to go to real time. I'm here to describe why a lot of people have already gone to real time. So this is already happening. It's already happening for some time. I'm here to now describe some of the reasons why that's happening. So I think the first reason, and by the way, different reasons apply to different use cases, different teams. So they don't apply to every single use case out there. So the first reason that applies to some use cases is you literally have decisions that depend upon things that are happening in the last few seconds, last few minutes. That's the very definition of the problem that you're trying to solve. For any of you who have worked on risk problems or fraud problems, if let's say malicious actor gets access to your credit card, or maybe gets into let's say some account, they might stay dormant for a while, but then they might make a bunch of transactions very quickly, often in a few seconds, in a few minutes, but not more than that. The reason for that is if they try to do it slowly, the users would notice, they would block the card and they would not be able to do anything with that whatsoever. Ironically, the most predictive signal, if you were to write a model for this, is exactly this. If you notice that a lot of transactions have started happening, let's say in the last 1 minute, or if you look at the average transaction amount, let's say in the last 1 minute, and that is very different from, let's say, the average transaction amount, let's say in the last 6 months or 9 months or some period of that form, then you can be relatively confident that this is, abnormal behavior, and you have good reason to potentially block that transaction. Obviously, in a machine learning model, you'd probably be using GBDT or neural nets, and this will just be one of the many features and may not, unilaterally control the decision. But still, this is an important signal in this particular case. And if you're computing features once a day or once a week, there's just no way you'd be able to capture this. And so your models would completely miss out on very important piece of information here. I just give you one example. The same thing happens in a lot of different domains as well. So in the domain, where I come from, which is, recommendations and ranking, a very common thing is someone goes in, they take a bunch of actions all at once. Let's say people try to clean up their follow graph on Twitter, as an example. And you'd want your feed to, reflect relatively quickly after that. And, take into account all the new things that you just did. If it doesn't, there is no feedback loop for the user, then they would stop doing that altogether. And that's a decision which very much needs to take into account all the things that happen, let's say the last 3 minutes, as opposed to only, running once a day at midnight, and they're completely oblivious to all of that. Again, this does not apply to all the use cases out there, only to some of them. Here are some more reasons which may apply to some other use cases as well. In a lot of machine learning systems, cold start is a pretty challenging problem. So let's visualize one particular scenario. Let's say user just signed up, and we know very little about them. And if let's say we are still in let's say batch-oriented stage 1 world, we would need to wait for the next time the pipeline runs at midnight. We'd need to wait for the next midnight to process whatever little we know about them, and then convert that into features and model signals. And that basically means that until then, the user might get no personalization whatsoever. You might then hack that by writing some rules on top of that, writing some heuristics. But what you're really doing at that point of time is writing a poor man's version of a real-time model, except it is not done through machine learning. And for anyone who's worked on any consumer product, you know that the user retention drops extremely rapidly in the first couple of experiences with the product. And if you're not giving people a good experience when they sign up, or within the first hour of that, the chances are they are never coming back to you. And so that is literally the moment when it is really important to give people a good personalized experience, when batch oriented systems are unable to do so. The same thing happens on the content side as well, by the way, or product side as well. So if, let's say, imagine you writing a post on Facebook or Instagram, or uploading a video on TikTok, and you are eagerly waiting to watch the likes drop in, but there are no likes for, let's say, 24 hours, because the distribution system, the ranking system that decides what content to show to people, that refreshes only once a day, let's say at midnight. And until next midnight, your content isn't shown to any, like, that's clearly not a good experience whatsoever. Even if you have cases where people, this is not the first time they're coming to your product. For a lot of people, there's usually a long tail. You have very little data points about them. Let's say you have 2 data points about them, in which case being able to do this real time significantly increases the amount of information you have about the user from the very last interaction they did. And in practice, it turns out that it leads to pretty large increase in the user experience, which then leads to improvement in metrics that people care about. Here's another reason which applies in some other domains and some other use cases. If you have a use case where you are trying to cater to non-registered users, where you do not know much about the user, this is the first time you're seeing the user, and you very quickly have to make a very important prediction about them, you just absolutely by definition cannot pre-create things, pre-compute things. You have to do it on demand. A very powerful example of that is insurance. When you go apply for insurance, hopefully the insurance broker does not have data about us. Hopefully they do not know my SSN or my credit score. And even if they do know that, there's a bunch of information that I provide when I enter my information in that insurance form. A broker cannot afford to pre-compute everything for every user out there. They're just playing crazy. And so they absolutely have to make decisions and predictions based on the information the system got just literally 5 seconds ago. And this isn't like a pattern where if you have a domain of a vertical use case where you have to make decisions for non-registered users, you'd almost have no choice but to fall back to somewhat of a real-time system. In-session personalization is a variant of that, but it is actually very, very interesting. I think the way I describe this is, all of us are multifaceted. We have, different preferences, different interests, and also different needs. And you may have a, beautiful personalization algorithm that understands the user really, really well, understands all their, bazillion niche interests. But when the user opens your app, they have a particular need to satisfy in that very moment. They have a particular mood at that point of time. And you cannot afford to keep showing them generic content that that they are usually interested in, forever. Let's say maybe they are opening the app on a weekend, and in this very moment, all they want to do is watch mindless videos that are about cooking, as an example. And you can, in the beginning, maybe the first 5 impressions of content you give them may not be about that, but it will be extremely tone deaf of the product to not listen to user feedback and continue showing them, let's say, sports videos as an example. And so in-session personalization is a pattern which once again applies to certain use cases. And when it does apply, then it matters quite a lot. And in those cases, that's a very good reason for people to want to try out real-time things. I've given you 4 reasons so far. I now want to shift the gear a bit and give you some reasons that are more around the infrastructure, the implementation side, as opposed to the business use case. So one very interesting dichotomy here is around cost. I think it is widely believed that real-time systems are costlier to run, costlier to build, and it is definitely true that the cost of per unit computation on real-time is higher than, let's say, a well-optimized batch system. But the problem with a lot of these systems is you do not know what decisions you're going to have to make, let's say tomorrow, let's say in the next hour. And so what then people do is they fall back, if you're still in the offline world, that is, you fall back to pre-computing every model prediction for every user, every combination of inputs out there. And in practice, almost all of that is futile. Almost all of it would never be looked at even once. And you rerun the exact same computation, next hour, next day, which would also be futile, and we continue doing so. And so a very, very large amount of computation is wasted. But you're not only wasting computation, you're also wasting storage, because you have to store all these features and all these predictions for everyone out there. So it's a very real story. At some point of time, LinkedIn used to, they still have this, recommendation for people you may want to follow on the right-hand sidebar. And as it turns out, it is an order n squared problem, because it is, personalizing, to the viewer based on the profile that you are on right now. And they could only run, 2 or 3 variations of that A/B test at any point of time, because the storage cost was so prohibitive that you just cannot run a bunch of those at any point of time. And so I think what we have seen is at smaller scales, the cost often doesn't matter, whether it is real time or not. And when it does start mattering, then real time ends up being cheaper if your application, fits a particular kind of pattern that we have described so far. Here's another one, which is very, very counterintuitive. But once you, experience the experimentation velocity of real-time system, you'd never want to go back. Let's say you set up a daily pipeline, everything is good. And you go back home and you find out that there is a small bug. Fixing that bug itself is only going to take you 15 minutes. But the pipeline only runs once a day. And now, since you missed the deadline, so to speak, now it is going to run tomorrow only. A typical A/B test in a lot of these cases is 7 days long, or 14 days long, depending on what domains and how much data you are dealing with. Let's say it is a 7-day long experiment, and you wasted 1 day because of a 15-minute bug. That is 15% slower iteration velocity, just because of one bug. But in practice, what happens is a couple of those happen for a lot of these experiments. You maybe set up some experiment, you discover from user feedback that something's going wrong, you go back, you fix that thing, you then restart your pipelines. It takes a day for the pipelines to catch up. Then you can start your experiment, and you're basically wasting a lot of iteration cycles in this whole process. It is also, and this is very important, it is very, very hard to debug an offline system in A/B testing setting. Let's say some bad recommendation was shown to a user, or let's say bad credit scoring decision was made, or let's say like a transaction was permitted that should not have been permitted. And our jobs as data scientists, machine learning engineers, is to go back and improve that model again. And so we need to build up an intuition on why is model behaving poorly in the first place, so that we can then go back. We inject the right feature, do the right hyperparameter training and things like that. But good luck debugging an offline system. You have a pipeline jungle, lots of airflow jobs that all create some data, and at the end of the day, you get a prediction, and that prediction is not good. How would you even know what created that thing? The way software solves this problem in general, if you move out of machine learning as a domain, is you can kind of recreate that specific request all over again and trace it at each step to understand what is happening in each step. But that you can only do for a real-time system. You cannot do that for a batch system at all, by definition. And finally, the last observation that I've seen in several places by now is a lot of these stacks, they start as offline because it is believed to be simpler to use, simpler to write, simpler to operate. But then more and more patterns are added to this over time. More and more failure cases are added to it over time. Maybe most of your system is batch, but then your product manager comes to you and tells you that you absolutely have to filter out deleted content. So then add a filter on top, but that filter is talking to Postgres so that you can filter out things in some real-time thing. Or maybe let's say you decide that there's a business rule that this kind of demographic should basically see this kind of a thing, or there's a sale going on, or you want to apply a discount of some kind. All these small band-aids add over time. And what started with like an clean offline system ends up becoming a Frankenstein of very, very complex moving parts, until it becomes so complex to iterate upon that it collapses under its own weight. By contrast, if your stack starts as real time, in the beginning, the complexity can be higher, but that complexity does not grow from there. Why does it not grow from there? Because of the debugging point I mentioned earlier, because you can literally go back and retrace any single request and understand exactly what happened. So all the tools developed by software over the years, they come back into your picture. All the tools that have been developed, all the best practices that have been developed for web servers, as an example, they come into the picture, and you can utilize that to keep your stack much simpler. So so far, what I've described is there are different stages of real-time machine learning. Different companies are in different places in that journey. There are some properties of use case that push it towards being more real-time, and there are some good engineering infrastructure concerns as well. I want to take maybe a few minutes to also describe how does Fennel fit in with all of this. For those of you, by the way, how many of you have done feature engineering? At your day jobs, or okay, few of you have done that. Feature engineering probably is a mess at your places too. If not, please tell me how you do it so that we can, go build a tool for the rest of the world around it. But one common challenge with feature engineering is you're operating on data that is coming from lots of different sources. You have some data in S3, some in Postgres, some in Kafka, some in BigQuery, some in Snowflake. All of these data sources have their own modality. They have certain performance characteristics. They have certain update frequency. They have their own tools that operate upon them. And what you really want to do is somehow process it all together. Maybe join them with each other if you can, and serve the features and serve them back to the end user. Sometimes offline, sometimes online. And you want to do this in a way that feature onwards, there's a lot of uniformity. There's a standard way of writing features. You get good deployment practices. You can catch feature quality problems. But below the data layer, it's all a mess. As a result of this, what happens is the code quality becomes quite poor. There are multiple versions of the same feature, and iteration cycles become really slow, which then leads to a lot of correctness problems. Your features become corrupt. Maybe all of a sudden, without you realizing, features become null, and your model predictions are completely bonkers at that point of time. It slowly degrades. You don't even find out about this. It's not like anything breaks per se, but that happens all the time in a lot of these cases. And this becomes really bad the moment you inject any bit of real time. So when we say real time feature engineering, we are not talking about everything being real time. We are talking about, let's say, you have 100 features, 5 of them need to be real time, and the other 95 do not need to be. The moment you have even that, you are then in a different zone altogether. In the fraud example, your fraud, user transaction activity is coming in, and let's say you want to aggregate how many transactions happen in this city or on this ATM. So you have to essentially join that, Kafka stream that is coming in with some profile information that is stored in, let's say, Postgres, and then serve it back to the user. Remember, the budget for all credit card scoring is 100 milliseconds. So you probably get 7 milliseconds for feature engineering. You have to serve it back in that amount of time. That becomes really hard. And so what we provide you, we are building a tool which lets you connect all your data sources, and you can operate on them in a single abstraction. I like to joke that we are building an abstraction so beautiful it makes you cry. And once all your data is in the same place, you can then do feature engineering on it, and it's pandas native, Python native, and it can run inside your cloud as well if you have, let's say, privacy sensitive data. We manage everything. You don't have to do anything. You don't have to install. You have to install a Python client using pip, but that's it. After that, you don't have to install or run or manage anything whatsoever. And the most interesting part about this is the exact same abstractions operate on batch data sets as they operate on real-time streaming data sets. And what that means is you don't even have to think about the complexity that comes from real-time. You just write your features assuming you have a giant data frame. In practice, it's not going to be a giant data frame. In practice, it's going to update every second as new data arrives. And you still automatically make it work in some form. We also care a lot about enforcing good best practices. So there's a bunch here. I wrote a few of these in the last few minutes as we're preparing the slides. You want to have type schemas to catch problems. You want to have native support for unit testing, integration testing. By the way, with offline pipelines, that's another thing that's really bad. It's very hard to test them. It's very hard to do good CI/CD on that. You'd want to be able to write expectations against your features. Some of you are probably using great expectations. You probably want your features to be immutable and versioned so that there is no probability of someone going back and changing the definition of a feature without a code review at the very least. And you want a bunch of governance best practices like ownership, lineages, audits enforced as well. So we do all of that while taking care of data being present in large number of different disparate data sources. We have people using this in production, but these are still early days. And so if you'd like to, try this out, maybe, share some feedback, somewhat shape the direction of the product, please reach out. My email address is in the last slide that I'll show in a second. We're also gonna, open source this, or at least a large part of this in coming months. And so if you're interested in following along for that, you can find and follow our LinkedIn and Twitter, if you'd like. We are also hiring ML infra and generally people with deep distributed system background. We are literally building a streaming database here with bunch of layers of abstraction for machine learning on top. And we are building all of this in Rust, which is a very nice, cool language. If you have not written that, you should try this out. So if any of you are interested in that, please reach out to us. And that's all I have. Thank you. And this is my email. If any of you is interested in playing with the system, you can email me for this. Do we have time for a couple of questions, maybe? Yes, please.
I have two questions actually, but I already thought. So I'm curious, like, do you store the data in somewhere? So for example, if I want to do a retro on the price model, how can I do that? I'm not sure how it works.
You want to do a retro, you said?
Yes. So for example, if sometimes that we want to do a retro step based on the price model we run like for 2 months, right?
Yes.
How can I do that?
So first of all, we don't manage models or inference. We are purely a feature engineering platform. And one of the use cases that comes up in feature engineering all the time is, let's say I just wrote a feature and now want to train a model on that. What Facebooks and Googles of the world do is they log that feature data for a week. Within a week, they have a gazillion examples and they can train a model on that. Most companies don't have the luxury of that. So they have to, for a feature that you just wrote, go back in time and recreate what the value of this feature would have been at any given moment of time. So we do support that, if that's what you mean by retro, but we don't do anything with models themselves.
Okay, yeah, and I remember my second question. So do you handle model retraining here?
So we don't do anything to do with models. So the way we think of this is an orthogonal layer to model training and model serving, both of them. But for model training, or let's say retraining, you would probably want access to training data sets. And for that, you would need to go back in time and generate what would have been the feature vector for each of those examples. That we can do for you.
Is this for people actually?
We have some swag here. I didn't.
This is for the questions.
Absolutely, let's do that. We have a couple more, well, only just a couple more t-shirts and hoodies and socks here. So please help yourself along the way. But any last question?
No question?
Yes, please.
Terminology is kind of confusing to me. Not because English is second language, but because when you're talking about real time, we now mentioned real time kernel, which would need to be in order to really provide the real time services. And based on what I've seen in this example, I believe that this real time is an overkill. That's my opinion. However, talking on the financial side, because I'm actually for a weekend engaged in stock market activities, that's when real time of this kind would be significantly, I would say, more of interest and more useful than just interacting with opening an account with a bank. Like the way that they 2 hours, that's not a big deal, because I'm not going to buy a house in 1 hour or whatever. Simply let's over here if I understood the representation.
I think there are, what I'm taking away is 2 comments. Maybe the first one is, what is real time here, and the second one is is real time an overkill, or is it actually needed? So I think there are 2 elements of real time. The first one is data arrives and something changes within a few seconds after that, maybe a minute, maybe an hour, maybe a day, but it's the update frequency of the your features or models. That's one thing. The second one is the user is waiting and you have to give them something back, and even though the thing that you're giving them back has not changed, let's say in a day, but you still need to give that to them, let's say in 10 milliseconds. I think you're right that for a lot of people waiting for a few hours to open a bank account is fine. but there's also a large number of applications where that is simply not an option. If let's say you go and apply for an insurance quote, and a lot of that happens online these days, the expectation in the industry is within 10-15 seconds, you find out if you've been given a quote or not. If let's say you swipe a credit card, the expectation is within a second, either your transaction goes through or it does not. If you let's say open, let's say a personalization experience, the expectation is within maybe a second your app loads. You don't want to be waiting for that for a long time. And when it does load, it gives you some relevant experience. So I think all I can say is in practice, a lot of teams have found that when they move to real time, their business metrics go up. And as a result of that, they've already started doing that.
So I would like to add a challenge to you. Let's say I'm driving the car, my camera is noticing that I want to crash maybe in 400 milliseconds or whatever. This system ensure me just in that time period in between.
I think this system is only doing feature engineering. This system does not drive your car for you.
I'm just trying to say that same situation that will come up.
Absolutely. I think, and to be clear, there are some teams that are already at level 4, which are doing even more real time than I'm describing. And there are a bunch of use cases that are not there and would never get there. I think that's completely fine. I think the point of, to me, our perspective is there's a shift happening. And when we look back, let's say 4 years, 5 years from now, we then find that a very large fraction, but still not 100%, a large fraction of use cases by then would have become real time. Anyway, any last question? Yes, please.
What kind of scale can you operate at? Like what customers do you have right now that are pretty significant?
I cannot. I think our customers would not want to share their names, but we have let's see, we have operated at a scale of I'm gonna say at least 10 billion plus feature predictions a day, and it's built up in a way that it is all horizontally scalable. And so you can throw in more machines and everything would work. Like we've literally architected this in a way that there is no single point of bottleneck that cannot be horizontally scaled. I think my time is up. Thank you.
We have one more question on the online. I want to give you the opportunity. So you just click the chat. It's on the chat. So. Yeah, to the bottom.
The question is, for legal reasons, we need repeatability and reproducibility. Can that be accomplished with a real-time pipeline? Absolutely, it can be. So I think the difference between a batch system and real-time system, if you're theoretically thinking about this, is just the update frequency. There's nothing magical about a batch system that gives you repeatability. What gives you repeatability is the fact that you're versioning your data sets and you're making them immutable. You can make your batch data sets immutable or versioned, and you can do the exact same thing for real time. In fact, that's exactly what we offer as well, which is you can literally go back in time and know what would have been the feature value at this time. And we can do that because we very carefully keep everything to be mutable and in a version. All right, I think hopefully that answers the question. And I think my time is up. Thank you so much, everyone. Really appreciate that. And help yourself.